So, in today's class what we are going to do is to recapitulate on what we have covered in the last class, and then think about the components of pressure drop or the additional terms for pressure drop in microfluidic devices or microscale devices that one has to incorporate in order to find out the exact pressure drop for such systems. So, I will talk about heat pipes in relation to main issues of successful microstructure, and what we have seen in the last class is that the wall heat conductivity can play a major detrimental role in heat transfer in microscale devices. And while discussing the wall heat conductivity, we introduced the concept of heat pipes, and there we saw that heat pipes are essentially devices which are extremely efficient in transporting heat from one end, from the hot end to the cold end, and it works on capillary suction through the wicks which are providing micropores present in the system, and through the micropores, through the wick, the liquid will flow from the cold towards the hot side. When the liquid reaches the hot side, by suitably selecting the liquid, it will evaporate at that point and take the latent heat with it, and the vapor formed will travel in the reverse direction towards the cold side and condense there, releasing the latent heat. So, that is how the heat pipe will work. It is a passive device in the sense that there are no devices, no external devices which are used to make the liquid flow from one side to the other side. Everything is governed by capillary forces. Now, a variation of this heat pipe, when specifically used for microscale cooling, is the micro heat pipe. The genesis of micro heat pipe came while trying to cool the computer chips or the integrated circuits to within their operating range, operating temperature, which is about 85 degree. The major bottleneck was how to reduce the size of the heat pipes, and the main contribution to the size of the heat pipes was the presence of considerably thick wick, which has to be provided to account for the capillary suction necessary for the fluid to flow. So, we have to get rid of the wicks, and the methodology used was, instead of wicks, provide corners. So, if corners are provided, then the liquid will fill partially at the groove, let us say the corner at one end of the heat pipe, and at the other end, let us say towards the hot end, as the liquid progresses, the film, the meniscus will be depressed more and more towards the corner, towards the apex of that corner, and this would result in a difference in curvature. So, this difference in curvature would in turn result in a difference in the liquid pressure, because we know that the liquid pressure for a curved meniscus is governed by Young-Laplace equation, and the Young-Laplace equation simply tells us that PL, which is the liquid pressure, is equal to PV, which we can consider to be uniform throughout the heat pipe, PV minus sigma k, where k is the curvature. So, let us say we are discussing about two ends of the heat pipe and these are connected, and over here it is almost filled with the liquid, and towards the hot end it is depressed towards the vertex, towards the apex of the groove. So, the PL, and we will assume that the PV is about the same everywhere. So, PL would simply be equal to PL at point 1 would be equal to PV minus sigma k, sigma being the surface tension and k is the curvature, which is related to, which is about 1 by r, where r is the radius of curvature. Now, if we see in these two cases, the curvature for case 1 is going to be substantially smaller than curvature for location 2. So, this is my location 2 and location 1, and as a result of this, we would see that PL, pressure in the liquid phase at location 1, is going to be greater than P, the pressure of the liquid at location 2, and this delta P equal to PL 1 minus PL 2, this would be the driving force for liquid flow from the cold side towards the hot side. So, this is how the micro heat pipe will operate. Now, additionally, we were also discussing about, I think we should go slightly deeper into that in today's classes, where exactly is the evaporation taking place. These sides are hot, let us say this side is hot. So, the entire solid is hot. So, there a possibility of evaporation is from here as well as from the thin film that extends along the walls of the micro heat pipe. So, if I blow this region up, then I would see a situation which is something like this. Okay. So, this goes towards the capillary meniscus part or the region where the curvature is constant. This is called the macro part of the meniscus, where the curvature is given by simply 1 by r, r being the radius of curvature. But as we move along the wall, then we will come to a point where the liquid forms a very thin film on the solid surface, and the molecules of the liquid are attracted so strongly by the solid due to the van der Waals attractive forces that no evaporation is possible from here. Whereas, I am going to have substantial evaporation from a region which is called the transition region, and this transition region will account for most of the heat transfer, most of the phase change that is occurring in a micro heat pipe. So, essentially it is this region which will control how much heat is going to be transferred from such a system. And as we move towards the bulk part of the meniscus, as you can see, the distance from the hot wall is substantial. So, therefore, the conductive resistance is more, and we may not have enough evaporation or substantial evaporation from this. So, even though the entire interface is active in terms of heat and mass transfer, but ultimately the end process is controlled by what is happening in a region very close to the interface, very close to the interline, which is the junction of the solid, liquid and the vapor phase, where the thicknesses are very small, of the order of microns or even less. So, it is this region which one should scientifically look at in order to enhance heat transfer from the region. So, now we go into we went into the modeling of a micro heat pipe, but before that I have added few things in here, which is about what is the classical definition of a micro heat pipe. The concept of micro heat pipe came in 1984 by a researcher whose name is Cotter, and Cotter proposed that the corners can provide substantial or enough suction so as to have flow of liquid over at least a small distance compared to a macro heat pipe. So, we can have liquid delivered over a length scale of centimeters, and he has defined, this is the statement which is used for defining what is a micro heat pipe, is where the curvature of the liquid vapor interface is comparable to the reciprocal of the hydraulic radius of the total flow channel. So, this is probably the closest scientific definition that we can think of a micro heat pipe. The dimension is comparable to the radius of curvature. Okay, that is what is the definition of a micro heat pipe. And I already spoke about the basic mechanism of what is a heat pipe, and this is another picture which I have added to my last class. Is that this is a circularly grooved wafer made in 2006 at the Sandia National Laboratory, and what you can see, there are channels which will make the liquid flow from the outside, from the periphery towards the center. And even in the next picture you would see these channels are not just unique single channels. In these channels there are several other channels which are also present. So, this is the large channel which we were seeing in the previous picture, and this is a smaller channel. Okay. So, there are 3 or 4 such channels embedded into the large channel. The ridges provide more corners, sufficient corners for the liquid to flow from the hot side to the cold side. So, the sizes are about 10 to 20 microns, and the smaller ones could be as small as 5 microns in size. So, if we go back to the previous picture, here what they have proposed is they placed the IC or the heat generating component over here right at the center, and when sufficient small amount of liquid is placed along the periphery, the capillary suction will draw the liquid from the periphery towards the center, and when it comes in contact with the heat producing IC, it will evaporate. And another silicon wafer would be bonded on top of this. So it's going to provide that will not be grooved. So that's going to create the closure for these grooves, and through the grooves the liquid will flow, and some portion of the groove will be utilized for return of the vapor towards the cooler section. So this is how the entire process will keep on extracting heat from the center and towards the periphery. This is something which we have made here. This is also based on similar concepts. The center that you see, we are going to place a heat generating component in here, and these are made at here itself using reactive ion etching, but we couldn't go that small channels. We were able to get about 100 micron into 40 micron. These are U-shaped channels. So through the U-shaped channels, the liquid will flow towards the center, evaporate, come back, and so on. And these channels are closed using a Pyrex glass bonded on the silicon wafer. In the modeling part which I have described in the last class, basically the pressure gradient is provided by is caused by a gradient in the radius of curvature. So as long as we have a gradient in non-zero gradient in the radius of curvature, there will be some pressure gradient which will cause the liquid to flow. And this is the momentum balance equation. We also have the mass balance and the energy balance in the volume element. Compared to last class, I have added this term, which is previously what we were doing is the heat supplied to the element is equal to the evaporative heat leaving the element. But as you can see that as the packet of liquid moves towards the hot side, it's going to encounter hotter environment. So if that is the case, then the sensible heat content of the fluid packet will also change. So there should be a term which would account for the sensible heat gain by the moving packet of fluid while it's experiencing evaporation. So it's experiencing evaporation, at the same time sensible heat change. So this term denotes the sensible heat change of the fluid packet. But what we have seen through numerical analysis is that the order of magnitude of this term is quite small compared to the evaporative term which it should be. So we can even make it equal to 0 without much loss of accuracy. So the boundary conditions we have discussed already, and this is this is a figure where I would like to spend some more time. Now these equations are solved numerically for two different geometries experiencing identical heat transfer conditions. That means the amount of heat, the amount of heat supplied to the hot end of such a micro heat pipe is fixed for rectangular as well as for the triangular heat pipe. The sides are mentioned 400 and 800 into 400. And what we have done is the analysis is based on finding out the variation of radius of curvature with position, because we saw that the pressure gradient is connected with the radius of curvature gradient. So as long as we have a radius of curvature gradient, we do have a pressure gradient, and that pressure gradient will ensure that there will be some flow towards the hot side. But as we keep on increasing the evaporative heat flux, the capillary suction necessary to replenish the evaporated amount will not be available anymore, and that can happen when your radius of curvature becomes equal to 0. There is no change of radius of curvature beyond that point. So when we do not have any radius of curvature, that signifies that a dry spot has been generated, is created at some point near the evaporator. The moment a dry spot starts to form on a surface, the temperature at that point will shoot up, because there is no evaporative cooling available at that point. So we do not have any liquid coverage on that section, and if we go beyond that heat flux, then that dry region will propagate. So the critical heat flux of the meniscus is defined as the point or as the heat flux for which we are going to have the formation of the first dry spot. Now, the how much capillary suction a channel can provide would depend on, among various other things, the apex angle. Smaller the apex angle, you would see that the meniscus will have greater chance to go deeper into the channel, while still remaining a liquid coverage at that point. So, a triangular groove will work better than a rectangular groove, since the angle is going to be less for a triangular case. And this also can be verified by looking at the numerical results, is that for the same heat input, the change in radius of curvature of, let us say, TR1, the change in radius of curvature is relatively less compared to that of a triangular groove. Now, what you can see is that for RE1, for some value of the heat flux, the radius of curvature has come down to a point of about 0.2, whereas for the same heat input, the radius of curvature even at the hot end is close to 0.7. So, a triangular groove, I can still increase the heat flux to higher value, and the triangular groove will resist the formation of dry spot to a higher value. So, that was the point which I wanted to make in the last class, is that just looking at the radius of curvature profile would tell you how much heat flux, or what is the capacity of the heat pipe in terms of transporting heat from one point to other. And this is a plot of the critical heat input, or rather the dimensionless dry out length as a function of heat input. So, here you can see that up to a heat input of 0.02 watt, there is no dry spot for the case of triangular groove, triangular heat pipe, whereas let us say for about 0.1 we could see that there is formation of dry spot, and even with 4 corners compared to 3 corners of a triangular heat pipe, the rectangular heat pipe cannot be operated beyond a heat flux of 0.01 watts. Okay. And the dimensionless dry out length increases rapidly as I increase the heat flux. And so, this is from the theoretical study, and this is the definition of critical heat input, where the flow resulting from curvature change is unable to meet the evaporation rate at that value of heat flux. And here we see that some experimental results where the temperature profile is used to predict the onset and the propagation of the dry out point, where we see that the dry and wet temperature ratings are touching each other. We assume that it has reached a point where there is no liquid to the left hand side of that region, and we call that as the dry region. So, these two results can be compared, and but that is something which we do not need to know right now. And this is we would like to mention here, I would like to mention here is that even though the corners should be such that there will be liquid evenly distributed at all corners, but inclination will still have a role to play, because if you incline the heat pipe, then there would be an opposing body force which is acting on the flow. It is not going to affect the presence of the liquid at the corners, but it will affect the flow of liquid through the corners towards the hot side. So, this is what shows is that with change in inclination, how the critical heat input, the heat input that the heat pipe can sustain, keeps on decreasing drastically. And even here you would see the difference in amount of heat between the rectangular and the triangular. So, the points that is needed to be made is that there will be liquids at all corners, but the critical heat input will still be a function of the inclination. And we see in the next slide is how much is the body force with respect to the surface forces. We keep on talking in microscale devices that the body forces are rather unimportant. It is the surface forces which govern the flow, it is the surface forces which are important, and that fact is verified here by looking at the values of body force and the values of the force due to pressure jump at the interface, which is can be evaluated by the Young's equation, and there is an orders of magnitude difference between the two. So, the conclusions that we could make from this short presentation of a very complex phenomena is that the body forces are, I mean, their effects are rather small. In the liquid, there will be liquid at all corners, but the liquid will start evaporating at the hot end, and the liquid will be supplied by a capillary pressure gradient, and a point would come where the capillary pressure gradient would not be sufficient to make the liquid flow, and the profile of the radius of curvature can be used to predict the onset of the dry out point. Now, if you think about the operating limits of a micro heat pipe, there are essentially 4 or 5 different limits that you have to consider, and it may so happen is that the micro heat pipe is probably operating very well within the capillary limits, but it is not going to operate well at some other limits. So, a designer has to calculate all such limits, their possible values, and decide which one is going to lead to critical heat flux. The results that I have shown you before are assuming that we only have capillary limit present in such a case. So, we already know what is the capillary limit, where the capillary pressure head is less than the sum of all pressure losses present in the system. So, the moment that happens, you have reached your capillary limit. Okay. And there are some approximate formulas which would give you, these are approximate relations, I would say these are correlations again proposed by the pioneer in this field, Cotter, which tells us about what would the value of critical heat flux be, and where these are available at references, the expressions for KL, KV, HL and so on. So, we already know what is capillary limit. So, let us go to the next limit that one can think of. It is called sonic limit. Now, if you increase the heat flux to the system, to the evaporator, vapors are going to be generated. The amount or the volume of vapor generated per unit volume of liquid evaporated is quite large, it is very large. So, through the channel available for the vapor to flow towards the condenser section, it is going to travel at high speed towards the condenser. The speed of the liquid, the velocity of the liquid would be rather small, but the velocity of the vapor can be very high. So, a point may reach at certain value of heat transfer is that where it has reached the sonic limit at the end of the evaporator channel, evaporator section. So, the moment it reaches sonic limit, then further addition of heat flux will not increase the velocity of this, and this would lead to a clogging, and this clogging is known as the sonic limit, which could be possible for situations in which you are dealing with very high heat flux cases. The second is entrainment limit. Now, if we think of, let us say a solid, and I have a liquid on top of it, and I have some flow of vapor. The liquid flows in this direction and the vapor flows in the other reverse direction. So far what we consider is that there is no momentum transfer across the liquid vapor interface, but that will not hold good if the vapor velocity increases. So, if the vapor velocity increases, the first thing that would happen to the interface is, instead of a straight interface, it is going to be a wavy interface. So, the waves are going to appear at certain point beyond if the velocity of the vapor is increased beyond that point, then the waves are going to be longer, and after some velocity the top of these waves are going to be sheared off, and this sheared off liquid droplets will come into the vapor phase. Okay. So, and these liquid droplets are going to be entrained by the vapor from the cold side, from the hot side to the cold side. So, liquid before it reaches the hot side, part of it is going to go back to the cold side without undergoing a change in phase. So, when this entrainment happens, it is going to limit the heat flux that the heat pipe can handle, and the entrainment limit again can be estimated by a rough formula. Also, this is something which would happen only at those heat pipes which are operating at very high heat flux condition. So, entrainment and sonic limits we do not encounter very often in micro heat pipes, only for those heat pipes which are operating at very high heat flux, and those are for standard or macro heat pipes, mostly not micro heat pipes. But at the other end we have a situation where, let us say, the operating temperature is quite low, okay, and we have a very small vapor pressure difference between the two sides. So, the very small vapor pressure difference and the slow motion of the vapor molecules from the hot side to the cold side. So, there is going to be sufficient viscous losses, and the viscous losses may exceed the vapor pressure difference that is provided in such a heat pipe. So, the viscous forces within the vapor region can be larger than the pressure gradient caused by the imposed temperature field, and there is going to be it's applicable for cases where it is very slow moving. So, slow moving vapor towards the cooler side will give rise to viscous limits. In this no flow or the low flow condition in the vapor region is called the viscous limitation. And as you can obviously see that this is the chances of viscous limit being the limiting phenomena in a heat pipe would appear only for cryogenic heat pipes, where the amount of vaporization is generally low, and there is again a rough estimate of a viscous limit can be obtained by utilizing this formula, this correlation. Now, the point I would like to make here is that one should calculate all these limitations while designing a micro heat pipe, see which one is the smallest or largest, which one is the smallest, and change the design criteria in an appropriate manner. But for micro heat pipes, it is a capillary limitation. Almost 90% of the cases, it is the capillary limitation which will govern the heat pipe, the performance of the heat pipe. So, that is more or less that I wanted to cover in micro heat pipes. It's a growing literature. There's enough information available in several fantastic review papers which you can read to know more about the operation, the design, the fabrication, the limitation, and possible uses, ongoing uses of micro heat pipes. Now, I am going to talk about the pressure losses that one may encounter at micro scale. Now, usually the flow inside a micro channel or a micro device is laminar. So, we know very well how to calculate the pressure drop over a certain length of the heat or length of the channel. But there are in some cases there are internals which are provided in the flow path, or there are bends in the channel, and those bends and internals can generate local vortices, and then the flow becomes turbulent or at close to turbulent. So, it is not there. So, there should be two contributions to pressure drop in such a system, one coming from the laminar flow and the other coming from the turbulent flow, with separate methodologies to handle each of them. So, the equations that I am going to show to you are very straightforward. They are just simple Bernoulli's equation and nothing beyond that. So, some form of Bernoulli's equation can be used to predict what would be or to calculate what would be the pressure drop in a micro system. But by rearranging the equation in different ways, one can clearly see the effect of smaller dimensions or effect of smaller length, effect of viscosity, and so on. So, that is something which so I am rearranging the very well known equation in different ways to give you ideas about the effect of size, the effect of property, and the effect of number of channels being added to the flow path, okay, and how they would depend on Reynolds number, volumetric flow rate, and so on. So, this is a very well known fact, is that we are going to have high pressure losses due to high surface to volume ratio for the case of small channels. since the surface area is more, the frictional pressure drop in a small system will be more. So, we would definitely prefer low viscosity fluids for utilizing flow in a micro channel. So, suppose I am using a micro channel for heat transfer, I will definitely prefer something with low viscosity, but at the same time I will also be looking for a liquid which have high latent heat of vaporization. So, a balance has to, and the high latent heat of vaporization fluids are also high in viscosity. For example, if you consider water, water has relatively high viscosity compared to glycerin, but the latent heat of vaporization of water is the highest among known fluids, among the common fluids. So, you would like to utilize water, but how do we deal with low viscosity? So, one way, as I was probably discussing in the last class, is to add surfactants to reduce the viscosity of the water and use it as a coolant fluid in such a system. In many of the micro scale heat transfer devices, you would see that they use liquefied ammonia, because the liquefied ammonia has very low viscosity. So, a common liquid choice for these kind of devices is liquefied ammonia at high pressure. But there would be cases in which just flow in a microchannel with water, in which reactions are taking place, okay, and the reaction medium is water. So, we have to deal with water in microchannels or even higher viscosity fluids in microchannel. So, we write the standard equation, the Bernoulli's equation, the pressure head, the kinetic head and the gravity head. Of these three heads, obviously we do not need to consider the last term, where the effect of gravity is generally small, negligible compared to other terms in micro devices. So, we do not take that into account. Now, the way the pressure drop in a complex, the key word here is complex channel arrangement, where you have, let us say, a T junction, or where you have just one micro channel which is getting divided into number of such channels. So, at this junction vortices are going to be formed. Suppose you have a device in which a sensor is kept inside a flow. So, you have liquid coming in or a fluid coming in, and then it flows like this, creating a low pressure side over here and a high pressure side over here. So, these presence of these internals would create localized turbulence, which has to be taken into account. So, the standard formula for pressure drop can be enhanced by incorporating two terms, one which refers to the standard laminar pressure drop. So, lambda refers to the channel friction factor when the flow is laminar, when the flow is through a straight pipe, whereas this stands for presence of internals, or wherever vortices are going to form, wherever you have a bend in the channel or wherever the channel is divided into a number of sub channels. So, these two will have to be, the relative importance of these two terms will have to be taken into account, and let us see how it can be done. If we have low Reynolds number flow, obviously the second term should not be there in the expression. If we have high Reynolds number, obviously the first term becomes unimportant, though the chances of this happening is rather small. But the tricky part comes where the Reynolds number is greater than 10, but less than critical Reynolds number for that specific case. So, the common estimate of the value of pressure drop is by a square feet between the values of friction factors at laminar and turbulent flow, which is commonly used for predicting pressure drop in microscale devices. Now, let us look at this value of this friction factor in terms of CF, the friction factor that we know, and here you would see that the channel friction factor is inversely proportional to the channel diameter, and this is the reason why you have substantially high pressure drop in microscale devices, since your DH, the DH influences the value of the friction factor to a great extent. I would one can rewrite this expression, and let us say that we have a situation in which the flow is through long straight channels. So, the effect of this term is negligible, and you can see that the pressure loss changes almost linearly with velocity W, linearly with viscosity and with the length, but inversely with dH. Okay. So, smaller the value of dH, you are going to get higher pressure drop. So far it seems that it's simply linearly proportional to dH, but if we look at this expression in a slightly modified form, what you would see is that if I express everything in terms of Reynolds number, there would be a first term which is linearly dependent on Reynolds number, but a next term which depends on Reynolds number square. So, for systems with curved internals or systems where you would expect very high with turbulence, a small change in Reynolds number can lead to a large change in pressure drop. Similarly, if you look at the presence of dH square over here, this also tells us that how sensitive delta P is to the size of the microchannel. Now, these are important parameters in the design of a microchannel, because you can reduce the size of the microchannel. With the available fabrication technique that is with us currently, a size below 10 micron is not a big problem anymore. But how do you force the liquid to move from one point to another in such a system? So, that what kind of a pump are you going to use to have such flow and prevent leakage at the same time? So, there are different ways to fill the microchannel, different ways to cause flow in a microchannel where there are bends in the path. So, you would see that electric field is applied, the exotic applications, exotic body forces are being applied to make the liquid flow from one point to another. Okay. So, electric field is one example, but that would give rise to interesting effects such as electrokinetic effects. What happens to the viscosity when you use electric field to move a liquid from one side to the other? Because the electric field near the liquid solid interface would create ordered structure in the liquid molecules. So, the apparent viscosity of the liquid will be much more than the actual viscosity of the liquid. So, you are dealing with glycerin, but near the wall, the liquid wall, due to the presence of due to the ordered structure of the electric field, ordered effect of the electric field, the viscosity is going to be much more, viscosity of glycerin will be much more near the surface. So, this apparent viscosity is going to give rise to a very high pressure drop. The pressure drop that you calculate using bulk property will no longer be applicable. So, these new sciences have come up when you have flow in a small system, and these equations, or the equation that I am going or the rearrangement of this equation simply magnifies the effects that one should consider while thinking about flow or how to make liquid flow in a microchannel. So, with decreasing device length dimensions, as I mentioned, the pressure loss is proportional to the square of the Reynolds number. The moment you start decreasing the device length dimensions, the first part becomes unimportant. It is the second part which is going to govern how much pressure you are going to have. If you have a number of internals, if you have n number of rectangular parallel channels, then the volumetric flow through such channels can be expressed is going to be obviously proportional to this dH square will be the flow area, W bar is the velocity. So, this is essentially the proportional to the volumetric flow rate, multiply that with n and you get the total volumetric flow rate through a series of through a number of such channels connected parallelly. But this expression that I am going to show is valid only when we have a single manifold. You have one manifold and then the liquid is going to get divided into n number of channels. The subsequent equations are valid for that. So, you have a system, when you express it in terms of this expression, then interesting things that you would see. you look at the last term in the denominator, dH to the power 4. So, any small change in hydraulic diameter of the system is going to increase the pressure many times. Okay. So, this is something the designer, the fabricator will have to be very careful about. So, now if I look at the number 2, the convective part, the convective pressure losses depends on the square of the volume flow rate obviously, but the hydraulic diameter, it plays a very crucial role in because of the inverse dependency of the fourth order. So, one has to think about the higher pressures which are possible, and there are certain obvious facts or obvious observations which one can make is that when we have a very short microchannel, the pressure loss may be low, but the reduction in pressure loss can be more than offset by certain chemical reactions which may take place in shorter microchannels. In shorter microchannels, the mixing is going to be very good. So, if mixing is going to be good, and if you have a reaction, let us say a polymerization reaction that is taking place inside a microchannel, what may happen is that the rate of polymerization will increase, the formation of large molecules will be more, the chances of precipitation will be more, and the precipitated large molecules can clog the channel. So, one has to the option of limiting the length of the microchannel when you are utilizing it for a polymerization reaction is one example which leads or which points to the complexity of different processes that one has to think of while designing such a microchannel. So, simply by reducing the microchannel, you may not get enough leverage, you may get some reduction in the pressure drop, but the resulting reaction and the deposition of particles can give rise to higher pressure drops. But with all these difficulties, I should also point out that for gas flow microreactors, not liquid flow, it is for gas flow microreactors, the pressure loss is small, at least about 3 times smaller than that of macro reactors or fixed bed reactors, with all the advantages of microscale processes. That is, the conversion is going to be much more, the yield is going to be much more, and you can suppress undesirable equations by proper design of a micro reactor. So, that is why in recent days the micro reactors are gaining more and more importance compared to macro reactors, but essentially the flow in such devices are so complex that it is very difficult to control them. So, several things one has to keep in mind while designing a micro reactor. Now, the third point that I would like to discuss about, it is pretty obvious, straightforward, is that surface roughness can play a very dominant role in microchannels. Any idea how much should be the surface roughness of a normal pipe? Orders, angstrom, millimeter, microns. Just a pipe which is carrying household water, drinking water, it could be microns. Okay. So, we are talking about a 1-inch pipe which is carrying water to us, and the scales that form in or the surface roughnesses that are even present in a very new pipe about 100 microns. Okay. 100 microns for a smooth pipe. Now, 100 microns to 1 inch, it is not comparable at all. Okay. So, whether or not you have roughnesses can create change the friction coefficient, but it is not going to change the flow area. But suppose you have 10 micron surface roughness on a microchannel, that is going to substantially alter the flow area available to you. I am not talking about friction factor, I am only talking about flow area. The friction factor will obviously be more when you have higher surface roughness, but the presence of surface roughness itself should point to that the diameter that you choose, diameter that you use for your calculation has to be substantially reduced. Okay. So, this is an additional consideration for micro channels, the corrosion, the fouling, etc., that one has to in order to take into account of that, the surface roughness has to be incorporated into your calculation. So, it is some problem. Essentially, let us say let us try to describe it, is that if I have a specific hydraulic diameter and epsilon being the surface roughness of such a device. So, we take the worst case, and when you have it is a rectangular channel, and let us say we have surface roughnesses from the top and from the bottom as well, and we subtract the surface roughness, the value of the surface roughness epsilon from the diameter in order to obtain the diameter to be used for real calculations. Okay. And corrosion also plays fundamentally, it basically kills the flow through the microchannel, and there are several applications where you would see that the number of times a microchannel can be used is also limited. Okay. So, you cannot use a microchannel for a reaction in which you have formation of particles, maybe nanoparticles, and keep on using it without cleaning, because cleaning of a microchannel is extremely almost impossible. How do you clean a microchannel? Okay. You cannot use a liquid jet to clean the microchannel. You probably would not be able to use a chemical to clean the microchannel, and any kind of physical cleaning, contact cleaning is impossible. Okay. So, your any corrosion, any material that you use for fabricating the microchannel, you have to think about the corrosion issues, which in a totally different way than when you are dealing with a normal macro pipe. And generation of particles, if you have a reaction which generates particles, then you should think carefully, you should think you should be very careful before making a decision of using a microchannel for such cases. So, reactions in which generally you have catalytic reactions, where if you could line the sides of the microchannel with catalyst particles and you can keep them fixed at that point, then probably it can be used. But situations in which solid particles are going to be generated as a result of some reaction, microchannel is definitely not the right candidate to be used for such cases. And there are situations in which particle may stick to the wall, and once they stick to the wall, they act as the nucleation site, and they attract more particles, and they create a colony of particles around it, and thereby increasing the value of epsilon, and thereby diminishing the value of dH even more. And the moment the value of dH diminishes, the value of delta P is proportional to 1 by dH to the power 4. So, for this, if you keep everything else same, even a very small change in dH can give rise to a very manifold increases in delta P. So, the effects of corrosion, the effects of particle generation, the effects of particle deposition, which we could be a bit casual about it in macro flows, it cannot be, you do not have that liberty in microchannel flows. In the places where this microchannel is going to be very effective is when I have heterogeneous catalysis with high exothermic or endothermic reactions. Since you can control the temperature so very well in microchannels, they are the ideal candidates to be used in such cases. So, to summarize, I can say that these devices, the microscale devices, the microchannels, they present us with many opportunities in terms of higher rates of reaction, in terms of higher yields, in terms of eliminating undesirable side reactions, in terms of temperature homogenization, very well control about what would be the final product and so on. But it has disadvantages and special requirements. The major disadvantage that one should think of is the pressure drop. How do you control the pressure drop? What would be the effect of pressure drop? How do you ensure that you have the same amount of flow through all the channels? That is, the designing of manifold in these cases is extremely important. How do you distribute? So, the design of the distributor is extremely important. There are fabrication issues which we are now familiar with. I think Professor Ganguly is also teaching you extensively on the different fabrication techniques. So, how do you fabricate, and not only fabricate, how do you make sure that you can have a repeatability in fabrication as you move along, and how do you ensure that the fabricated microchannel is going to be very, very smooth. Okay. There are different ways a microchannel can be made. For example, a lithography can give you a relatively smooth channel, but if you use, let us say, a wire EDM technique or reactive ion etching, these are different techniques which you would learn in part of this course. In all of these cases, the roughnesses on the surface can be maybe one order of magnitude smaller than the dimension of the channel itself, which would give rise to tremendous amount increases in pressure drop. In the special requirements about which are the processes that can take place in a microchannel, a catalytic reaction, possibly yes. A catalytic reaction where the catalyst particles can become loose from the side walls and start to move with the flow, definitely not. Okay. A reaction in which particles are solid, there would be precipitation, there would be formation of particles. These are the reactions which you will never try in a microchannel. But if you have, let us say, reaction of two reactions where they are diffusion controlled. So, two reactants coming in, two liquid reactants coming in contact where they are diffusion limited reaction. If you reduce the size of the microchannel, then the diffusion length and the microchannel length, when they become comparable, you eliminate a huge resistance for the mass transfer, and the entire process becomes much more effective. So, another problem would be, how do you make the liquid flow? You use electric field, you use normal pressure, normal pump, syringe pump, different types of fluid moving machinery, but how do you control such a flow? How do you ensure that you have right amount of flow through such microchannels? So, that is something which needs to be looked into for its successful application. So, in the next class we will deviate from microchannels and go into a system where we have an open surface on top of which I would like to make something move. So, I would like to use electric force, electric field to make certain amount of liquid to move from one point to another and the associated scientific issues. So, that electroweighting and digital microfluidics, that would be the subject of the next two lectures. Thank you.